All right. Um, Up to this point, we've talked about logarithmic and exponential functions. Earlier, we talked about inverse functions, but we're not concerned with inverse functions at this point. We are only concerned with exponential and logarithmic equations in this section. So we have a couple of principles I just want to remind us of. One is the principle of exponential equality, and the other one is logarithmic equality. The principle of exponential equality, you can see what I have written here. If you have an exponential equation on either side where the bases of the exponential functions are the same, then the exponents, the power on those, must be equal as well. The next principle is that of logarithmic equality, and that one too, suppose we have an equation where x and y are equal, therefore log of those must be equal too, because they're the same numbers, right? If x and y are the same thing, then their logs would be the same. And of course, I have here especially in the case of the logarithmic one, but really for both of them, these properties hold where they are defined. So we don't want to get into a case where, for example, the argument of a log is negative, and then we say, well, this works because the way the principle works. So here I have the restrictions that I place on a, x, and y. And I'm making them all positive here, namely because in the logarithmic form, remember, the argument of a log has to be positive because the domain of a logarithm is simply not. It is not all real numbers. The domain of logarithmic functions is where x has to be positive. That means greater than 0. Now with exponential equations, we don't have any restriction on those because namely the domain is all real numbers. All right, so that's really all we have in this section. We're going to work quite a few examples here. I think by the time I'm done, we'll be looking at least 10 problems from this section. So let's begin with something simple. Let's start with this example. Suppose my exponential equation is 3 to the x is equal to 7. Now we're going to encounter two types of exponential equation. One is, for instance, I have a to the x equal a to the y. Those are the easy ones, right? Where we equate based on the principle of exponential equality. We simply equate the exponents and we can solve them. And then we have other types of exponential equation like the one that I have listed. What if it's in the form of a to the x is equal to b, where b could be another expression, it could be a number, what have you. Notice I do not have two exponential functions. I only have one. So for these, there are several ways, by the way, we can solve any of the problems that I'm about to do. I'm just doing them my way. And it's really not my way, but it's a way that I think uses the less amount of brain cells. So in other words, I don't want to make it too complicated. So I'll try to do it in a manageable yet accurate way of solving them. So in the case of something like a to the x equal b, we can rewrite these expressions in logarithmic form. Remember? An equivalent expression in log, for instance, for this one would be log base b of a is equal to x, and that in fact solves it. So depending on which of these two types we have, then we get the appropriate action. So in this example, that looks like the one on the right. So I'm going to do exactly what I recommend. Let's just rewrite this in logarithmic form. So when I rewrite in log, remember the base in the exponential form becomes the base in the logarithmic form. And the number that's on the other side of the equal sign goes in front of g as the argument of log, and there you go, x goes by itself, and we have solved this equation. This would be the exact value, but let's say we want to find the answer to the nearest thousands in this. Okay, in other words, we want to estimate them. Again, this would be exact in the sense that I don't have to use a calculator. I don't know what the value is, but it's pretty, looks pretty to me, as long as I get x by itself. So that's exact in that sense. Now, if I want to approximate this to the nearest thousands, then because the base is 3, that means it's other than common log base 10 and other than natural log base e. Remember, we talked about change of base formula in another section prior to this one. So I'm going to use the change of base formula to use my calculator. So I'm going to write this as an ln of 7 over ln of 3. And then I can use my calculator, and when I do my calculator, that ratio ends up being 1.771. And that would be the approximated value, not exact, because I rounded it to the nearest thousands. All right, so there you go. That would be an example. Let's take a look at another example. In this next example, suppose I have e to the x squared equals to 100. Again, that would be of the second type, where I only have one exponential function and the other side is possibly another expression or a number, in this case 100. So let's rewrite this one. By definition of log, the base e is going to appear in the base of the logarithm. The number 100 goes in front of g, becomes the argument of the log, and the exponent on exponential form goes on the other side by itself. And there you have it. Almost solved, isn't it? And because I have log base e, remember again in the previous section that we calculated these logarithms, we can write log base e as a natural log. So that's just simply natural log of 100. To solve for x, we take the square root of both sides. We're using the square root principle. Anytime I use the square root principle, I do have a plus minus in front of the radical. So in this case, there are two possible solutions. Again, square root of ln of 300 would be exact, but we can also approximate it using a calculator. I did, and I got 2.146 plus or minus. So those are the two solutions that we have. All right. And I don't need to check the solution, by the way, because the domain of an exponential function is all real numbers. So unless I do something wrong, then I don't check them. Now with logarithmic equations, you will see I will check every solution, even though they may be trivial or obvious. Because the domain of logarithm is only, the argument of a log can only allow for positive numbers. Okay, and that's the argument of a log again. So we'll see how it turns out in a few minutes. Next example, another exponential function of this type. Suppose I have 1/3 now raised to the x power equals -3. Okay, if I rewrite this in logarithmic form, I get the log base of 1/3 of -3 equals x. And I just said that the domain of logarithms are positive numbers, correct? And check this one out. The reason is because if you look at -3 in the argument of log, that one is less than 0, and we are not allowed to have negative numbers. The argument of the log has to be positive. Therefore, for this one, we're just going to say simply no solution. It is not possible for this to happen. And we can also catch it in the beginning from the get-go right in here in the initial step. 1/3 to the x, if you graph this function, the graph of 1/3 to the x, because the base is between 0 and 1, it's going to be a decreasing exponential function. And for this one, if you noted, the y value, which is what the function is, f of x, is exactly this. It's always positive, right? There's no way the value can be negative. So we could have caught it this way also. But this thing about math always gives you options to do things more than one way. So however you do it, this one does not have a solution. There's no solution to this equation. Okay, let's take a look at another example for this one. in this next example, let me change my pen. Okay, in this next example, suppose I have 3 times 2 to the exponent of x minus 2 plus 1 equals 100. So I do need to isolate the x, right? The exponential function, which x happens to be in the exponent of. Therefore, I'm going to subtract 100 from both sides. That will make it 3 times 2 to the x minus 2. And notice how I have parentheses around 2 because without it, if I don't, then this may be mistaken by 3 times 2 as if x minus 2 is over the entire product. And that's not what we want. So that's the reason for the parentheses. Okay, so let me go on the next line and actually put this. This would be 3 parentheses 2 to the x minus 2, and I subtracted 100. Now I have 99. Now let's divide both sides of this equation by 3. And we get 2 to the x minus 2 equals, dividing by 3 on both sides. So I get 33. Okay, and now at this point, again, it's in the form of an exponential function on one side, a number on the other side. So for these, I translate them into logarithmic form. So that means I have log base 2, whatever base of the exponent, that will be the base in the logarithmic form. Equals of 33 equals x minus 2. So now I can isolate x, and to isolate x I can add 2 to both sides, and that would be 2 plus log 33 in base 2. And again, this would be the exact value, but we want to find an approximation or an estimate to the nearest thousandths. So once you plug in this, and remember the base must be 10, a common log, or e, the natural log. So at least my calculators can handle it. And let me do that. So I'm going to go through change of base and write this as ln of 33 divided by ln of 2. And now this will approximate to 7.044, rounded to the nearest thousandths. All right, and we have the answer to that one. And again, for exponential equations, I don't really check them. Only for logarithmic equations, I check them. Let's take a look at another kind of exponential equation. This time, let's say I have e to 2x negative 6, e to the x plus 8 equals 0. Now this one I can rewrite that e to the x, I can write it as e to the x, and then I can square that, right? So I'm just going to put square here, and then I have the remaining terms, correct? So let's put the remaining terms now. Negative 6 e to the x plus 8 equals 0. Now this equation, if you look at the general structure, it looks like it's in the form m squared negative 6m plus 8 equals 0, right? And here, acting as an m in this example is e to the x. So the point being that the underlying equation here is a quadratic equation. And in fact, this equation, the original one that I'm working with, these are equations that are said to be quadratic in form. Quadratic in form means exactly this. Means you can rewrite them in the form of a quadratic equation. Now, quadratic equations, remember, we can factor them if they're factorable, or we can use the quadratic formula on. And this one turns out to be factorable, so I'm just going to go ahead and factor this. The factored form would be e to the x, those would be my first terms, equals 0. Now I need two numbers that multiply to 8, and they add to negative 6. And the two numbers will be negative 2 and negative 4. The product is 8 positive, their sum negative 6. And then we can solve this one, right? We can set each of the factors equal to 0. So at this point, I say e to the x minus 2 may be 0, or e to the x minus 4 could be 0. And then move 2 to the other side. In the second one, add 4 to both sides. And now we have an exponential equation where you have an exponent equal to a constant. Remember that one? I can rewrite this in logarithmic form. The base would be e of 2 equal x. And the other one also would be log base e of 4 equal x. And if you recall again, log base e's, we call them natural log. So I do have a solution. In fact, the solution is ln of 2. And from the one next to that, the second solution is ln of 4. Again, these look just as good to me as if I approximate them. And I did. The approximation for the first one is 0.693, and the approximation of the second one is 1.386. And there we have it, the solution to that exponential equation. It has two distinct solutions. Let's take a look at another one. In this next one, suppose I want to solve the following. Let's take a look at now some logarithmic. Suppose I have 5 ln of x equals 0, and I want to solve this one. Actually, let's not make it 0. That's too easy. And the answer would have been 1, because ln of 1 is 0. Okay, let's make it 10. So to do this one, I need to isolate the natural log, divide by 5, and that's how I isolated the ln function. Now, to solve for x, I will translate this into an exponential equation. Remember, ln is log base e of x, correct? So I rewrite this in exponential form. That means x would be e squared. Again, that would be the exact value. And let's keep them exact from now on instead of approximation. The exact looks better. And there you go. That's the solution to this equation. That's it. Now, because I have a logarithmic equation, remember we always have to check. Okay, and what I'm checking for, I'll show you. You can do a full check. Let me do a full check on this one. And then later on, I'm not going to do a full check because it will take too long. I'll just check it, what I call a cursory check, to make sure the number is in the domain or in the argument of the logarithm. It's positive. So I'm going to do a full check on this one. 5 ln of e squared, would that equal to 10? Well, ln of e squared, using properties of log, I can bring the 2 in front of a log, write it as ln of e. ln of e is 1. That was from previous section. So the left side is 5 times 2. So that's 10, which is equal to the right side, 10. See, 5 times 2, 10 times 1 is 10. Therefore, it checks. All right, let's take a look at another one. All the next ones that I'm doing, all of these will be logs. This time, let's make this a log base 10. How about that? A common log. And in fact, because it's common log, I'm not going to even write the 10, just so we get used to not seeing that. All right. So here is a common log now because I removed the 10. And we want to solve for x. Now, in order to actually in order to actually be able to rewrite this in the form that we want, I need to put that base 10 in there. So I'm going to rewrite this as log base 10 of 2 minus x equal 0.5. Again, the reason is because I need to rewrite it. So what does that mean? This means that 2 minus x is equal to 10 to 0.5. Now 0.5 is 1/2. And 10 to 1/2, we can rewrite this one as the square root of 10. And then in the next step, we can solve it. Move x to the other side, bring square root of 10 to the left. And this will give me x is equal to 2 plus root 10. And that would be the exact value of this expression. Okay, so there is a solution. Now, I need to check to see if I'm in the domain of the logarithm. So here's my cursory check. This is my argument, right? The argument of a log is 2 minus x. I'm going to plug in the value for x, 2 plus root 10, and then minus, oh, that's, sorry, it's 2 minus x, right? So it's 2 minus, and then x is 2 plus root 10, correct? And let me make sure I got this right first of all. Oh, that will be minus. I'm sure many of you caught that one. I just did myself. So this is going to be negative 10. And then remove parentheses. I get 2 minus 2, that's 0. And then double negative on 10. Square root of 10 makes positive root 10. As long as it's positive, we'll accept that number. And there we have that. So the solution is a good working solution for this example. It checks. Now let's take a look at another example. Again, all my examples are logarithmic now. So here I have log base 3 of x plus 5 times x minus 3 equals to 2. All right, let's rewrite this expression. The rewrite of the expression would be x plus 5 times x minus 3 is equal to 3 squared, which is 9. Then I'm going to FOIL on the left side. We get x squared. The OI combination gives me 2x, and the L, which is product of 5 by negative 3, that's going to make it negative 15. I'm going to bring 9 to the other side so I don't have to rewrite it another step. Now, negative 15 minus 9, that's going to be negative 24 equals 0. And then this 2 will be factorable. The factored form would be x plus 6 times x minus 4 equals 0. From which we can solve, set each factor equal to 0 and solve. And we get x equal negative 6 and 4. Now, because this is a logarithmic equation, I need to check just to make sure the answers lie in the domain of the logarithmic function. So here's my check. And again, I'm doing a cursory check. So let's plug in a negative 6. And negative 6, where I'm checking is the argument. That's negative 6 plus 5. And then negative 6 minus 3. That makes it negative 1. Negative 6 minus 3 is negative 9, and the product is positive 9. Therefore, yes, that is a good working solution. Let's try 4. That would be 4 plus 5, and then 4 minus 3. 4 plus 5 is 9. 4 minus 3 is 1. That product 2 ends up being 9, which is positive. So both of these solutions are good solutions, working solutions. Again, all we're checking is to make sure the argument of the log is positive. Okay, and there you have that one. Now, in our next example, we have ln of 7 minus x plus ln of 1 minus x equal ln of 25 minus x. And also it's important, by the way, folks, when we substitute, when we verify the answers, we always go to the original equation to check it. And this is what the original is. We don't check them in equations that are in between, that are manipulated. That's very important to remember. So checking in the original, it worked, and that's good enough. Now, for this one, again, we do have the one-to-one property of logarithms, the principle of logarithmic equality that told us this. If two logs are equal that have the common base, call it b for base, then x and y must be equal. Now, the way this principle looks, it looks as if I can cancel the logs on both sides, and then I get x equals y, doesn't it? So some people, some students, people in general would think that. They would think that it's like as if I'm canceling the logs on either side, and that's fine. It works. Why not? But when you have more than one log on one side, that would be incorrect. In other words, if I say I'm going to drop the logs and go 7 minus x plus 1 minus x equal 25 minus x, this would be false. We are not allowed to do this. Okay, only when there is a single log on the left and a single log on the right, only then you can think of canceling these. So this would be incorrect. All right. So what is the correct way of doing this then? Well, the correct way is to combine the natural logs together. Because I have sum of two logs, so we can join them as a product. So sum of natural log becomes natural log of a product. The product is 7 minus x times 1 minus x. Equate that with natural log of the right side, which is 25 minus x. Okay. Now, at this point, and only this point, we can actually drop the logs, if you will. We can cancel the logs. See, I can do that. And then just equate the left side, whatever that is, and equal to the right side. All right, so let me do that. The left side, I'm going to FOIL the left side, by the way. So when I do, I get 7 minus 7x minus x plus x squared. And on the right side, we just have 25 minus x. Minus 5 minus x. All right. And then what do we do next? We need to combine like terms. So I get 7 minus 8x plus x squared. I'm going to move these two terms to the other side. Becomes negative 25 plus x equals 0. And now rewrite x squared. Negative 8x and x is negative 7x. Negative 25 and 7 is negative 18 equals 0. I just simply combine like terms. Okay, and the next step, we can actually factor the expression. This is factorable. So for the factored form, I get x minus 9 and then times x plus 2 equals 0. And by zero factor principle, we set each factor equal to 0, and that's how I get the solutions, right? 9 makes the first binomial 0 and negative 2 the second one. So those are, at this point, I'll call them the potential solutions. Potential because we haven't checked them. Let's do our check. And our check is just for the domain. I want to see if I'm in the domain of each of those. Now, because I have 3 logs, the proposed solution must work in every one of them, not just 1 or 2, all 3 of them. So let's try 9 for now. ln of 7 minus 9 plus. Well, ln of 7 minus 9 is negative 2 plus so on and so forth. And actually at this point, because the argument is less than 0, I can stop and discard that solution. That's not going to work because, see, it's going to give me a negative number for the argument of the log, and that can't be. We cannot evaluate those. Let's try negative 2. So next one, I have ln of 7 minus negative 2 plus ln of 1 minus x. So that's ln of 1 minus a negative 2 plus ln of 25 minus x. That's ln of 25 minus negative 2. And that's not a plus, it's equal sign. So I'm going to put a question mark because I'm checking. It may not work. We'll see. Hopefully it does. From left to right, the double negative on 2 makes positive. So that's ln of 7. Double negative on 2 again makes positive. That's ln of 3. Will that equal to ln of double negative makes positive? ln of 27. Let's see if they are. Using properties of logarithms, the multiplication property more specifically, I can rewrite the left side. The left side is ln of 7 times 3. Will that equal to ln of 20, or it should be 9, sorry, this one is 9, because you have 2 and 7 makes 9. So I have ln of 9 times 3. Would that equal to the right side? The right side is ln of 27. And of course, yes, it does. See how that worked? The value of -2 worked in all 3 logs. And also, this is actually a good example because we don't rule out a negative answer for x just because it's negative. Notice, a negative answer actually worked. We will actually use that as a solution. What we rule out are numbers, positive or negative, it doesn't matter, that will turn the argument negative. Now, a positive 9 in this case, see, the answer was positive, but we discarded it. The reason, because it made the argument of the log negative. So just because x is positive or negative, that's not the deciding factor. You got to plug them in. Sometimes positive numbers work, sometimes they don't. Sometimes negative numbers work, sometimes they don't. It just depends on the equation. Okay, so just want to emphasize that. This equation has only one solution, right? The solution set is just -2 for this one. Let's take a look at another logarithmic equation. How about this one? Suppose I want to do log base 5 of x plus 2 and then plus log base 5 of x minus 2 equals 1. Now for logarithmic equation, by the way, we have 2 types also. We have a type where you have logs on both sides. If you have logs on both sides, once you combine them, we will use the principle of logarithmic equality to solve them. But what if I don't have logs on both sides, like such is the case here? Well, I'm going to combine. I only have log on the left and number on the right. So I'm going to combine logs using properties of logarithms. If it's plus, you divide. If it's plus, you multiply. If it's minus, you divide them. So I'm going to go x plus 2 times x minus 2. Remember, if it's the sum of the logs, it becomes log of a product. And then at this point, we're going to rewrite them in exponential form. In exponential form, this reads x plus 2 times x minus 2 is equal to 5 to the first power. Now, x plus 2, x minus 2, that's the factored form of difference of 2 squares. So I'm going to write it as x squared minus 4. Or you can FOIL it like that and combine like terms. The OI goes to 0, and this is what you're going to get. So however you do it, the right side is going to be 5. Next, I'm going to add 4 to both sides, which makes x squared is 9. And then take the square root of both sides, I get plus minus 3. Remember, with the square root property, when you take the square root of both sides, you will have a plus and you will have a minus. At this point, I call this again, or these, potential solutions. But they're potential until we check them. So let's check now. Which one are we checking? Doesn't matter, we've got to check them both. When x is 3, the equation is log 5, 3 plus 2, plus, and remember, you always check in the original, not in the step 2, step 3 equation. 3 minus 2, will that equal to 1? See, first log is log 5 base 5. Second one is log 1 base 5. Will that equal to 1? In fact, we had both of these as properties in another section. Log 1 in any valid base is 0. And this one, if log and base, if the argument and base of the log are the same, then that log becomes 1. So the left side is 1 equal to the right side is 1. Checks. Therefore, x equals 3 is a good working solution. Now let's try -3. So this time x equal -3. Let's see if that checks. So I'm going to go log -3 plus 2 plus 2 base 5 plus log -3 minus 2 base 5. Is that equal to 1? Now -3 plus 2 is -1, right? In here, less than 0. We're done. As long as it fails 1, even if it works in here, which it won't. Even in here, it's -5. Fails both of them. All it takes is one of them, though, to fail. So we're going to discard -3. That's not going to be a solution. The only solution is 3. And this is actually a good one. Let me show you. I mentioned you always check the original equation, right? This was the original. The equation in the second step, when we multiply it, let's check it. Check the solution in that one. X plus 2, x minus 2, right? That's log x plus 2, x minus 2, base 5. Would that equal to 1? Remember, we ruled out -3 just now. It is not going to work. But let's try it in the second, not the original equation. In -3 in here. So this is going to be log base 5. -3 plus 2, -3 minus 2. So that's going to give me the product -1 times -5. And the product actually, -1 by -5 is 5, isn't it? Aha. And log 5 is 1. And it checks, doesn't it? You see what happened? -3 looks like it's working now, isn't it? But so what's the problem then? The flaw is right in here, because I checked it in that combined expression. Before we combine them, this is what they were. So it doesn't work in the original equation. It works perfectly fine in the second one. So I'm just going to cross this just to reiterate that you do not check solutions in between steps. You always check them in the original. All right, so this one we agreed the only solution is 3. Solution set has only one element in it. All right, let's do maybe, how about if we do one last one? Let's do one last one. And that'll be the end of this video. Natural log of e to the x, -2 natural log of e equals ln of e to the 4th. So again, I have logs on both sides, right? That would be incorrect. If I drop the logs and say e to the x -2 we cannot drop the logs unless there's a single log on the left, a single log on the right, which we are about to create. Let's do a single log on the left. Now, before we can combine these two logs, I'm going to move the negative, actually the 2, just the 2. I'm going to move it as an exponent on e. That's using properties of log. Which one? We have one property of log earlier in an earlier section. Log of x to the r base a can be written as r log x base a. So that's exactly what this 2 is. Its r is a factor in front of a log. Can move to the exponent in the argument of the log. And it just did. And there is the right side. Now, let's try. What do we do? Now we do the quotient rule. Okay, so this is going to be ln of e to the x over e squared equals ln of e to the 4th. Perfect. Now I can drop the logs. You see that? So from this, we're going to get e to the x over e squared is equal to e to the 4th. Multiply both sides by e squared. So we get e to the 4 times e squared And because of the product rule of exponents, common base, we add, not multiply, we add the exponents. So this is going to be e to the 6th. Therefore, e to the x is equal to e to the 6th. And from this, using the principle of exponential equality, we get x is 6. The original expression was logarithmic. So plug in a 6 in here. Let me do my check. ln of e to the x. That would be ln of e to the 6, and that checks. Again, what am I checking for? I'm checking that e to the 6 is positive. That's what I'm checking for. So that is a good working solution for this example. And there you have it. So hopefully you're comfortable with these equations, logarithmic equations and exponential equations. And with that, we are done with this lecture. I hope you find it useful. So if not, please review. We did a lot of stuff. We did a lot of good equations. So try to review them. And as always, thank you for watching the videos.